Whenever you're ready.
Alrighty. Hello, everyone. My name's Jack Lowry. Today, I'm going to be giving a little talk and a demo on how to use the navigation stack on ROS, specifically using SLAM and AMCL navigation. Can everyone hear me okay? Am I good volume?
Yeah, we can hear.
Yep.
Awesome, awesome. Okay, so uh, navigation is a pretty huge topic in robotics. It's still very much an open problem. And what I'm going to be showing today is just one implementation of it. Ideally, um, a lot of this code and what I'm going to be showing is direct from tutorials and stuff on the ROS website. But I kind of want to dive a little bit deeper into it and show you that if you were going to use any robot in any simulator, you would have the tools and the knowledge to kind of set this up and do it yourself. So that's kind of what I'm going to be walking through today. However, obviously, I need to choose a simulator, so I'm going to be using the TurtleBot, which is kind of little this cute little. It's literally just a Roomba with a Connect on it, so pretty simple stuff. Nothing really crazy going on there. And then I'm going to be using Gazebo as a simulator. So essentially, you just have a bunch of models in space and then a whole bunch of tools to simulate robotics. And we're not even going to be scratching the surface in Gazebo. We're going to be doing some really basic stuff. And I'm not really going to go into that either because it's not really what I want to show. But essentially, I'm just going to have TurtleBot set up running on Gazebo, and we're going to get all our sensor data, and information from there. Okay. Um, so yeah, prerequisites for using this stack. Like I said, I'm going to be using TurtleBot, but if you wanted to, let's say, use your own robot that you built in real life, or maybe there's other models and other kinds of robots that you want to use for this, there's a list of certain topics and other things that need to be published in ROS in order for all these programs to work. And I think we went over topics a little bit last time, but I'll just give a little overview. Um, Basically, a topic in ROS is just a piece of what's a good way to put it? Just like a topic where services can both publish and subscribe information to them, and it's generalized information. So let's say, okay, how about this? I'll take this as an example. One of the required topics for navigation is /scan. And this is the laser scan data from a LiDAR, which is just shoots a bunch of lasers out and reads the distance from the device that when those lasers bounce back. So /scan is a topic that can both be published to and subscribed to. So for example, my LiDAR might be a publisher. So every time it gets some information about, okay, I got a bunch of lasers that bounce back, here are the distances, it'll publish a message to scan, and then our algorithms will read that and use it to navigate and use it for a whole bunch of things. But the nice thing about ROS is it's platform independent. So this /scan topic, it can be published to or subscribed to by anything. Um, so if you have a totally different robot, it's kind of made for that, which is really ideal. Okay, so like I said, we need the /scan topic. That's really important. /ODOM. So this is going to be your odometry from all your sensors. Think if you have like an IMU or a GPS on the robot that kind of tells you your acceleration, that would be a component of ODOM, or the encoders on your wheels. So your wheels can kind of track how far they've moved, and you can use that information to estimate your position. That's going to be ODOM. And we need it as kind of like a base level of a base guess about where we are, but it's not enough to fully navigate ourselves around because it can drift really easily. So essentially our odometry is going to be like our first best guess, and then we're going to use a bunch of algorithms to actually solidly tell us where we are in an environment. And then finally /TF. So this is a list of coordinate transforms. So in ROS, essentially, you can have all your different pieces of your robot all modeled separately. So I got some images from a visualizer, and you can kind of see what I mean here. So in the image on the right, you can see you have the base, the little Roomba part of the TurtleBot, and the Connect. And each of these can be oriented like totally separate from each other. And the way that we keep track of all these separate components is through transforms. So The little 3 axes on these things, the green, red, and blue, those are like XYZ coordinates. And then by keeping track of the coordinate transforms between, like, for example, this Roomba and the Kinect, we can figure out the orientation of everything, and it'll help us keep track of everything and actually navigate well around the space. So 2 transforms are required. Everything else is optional, but in order to display everything nicely, we probably want all of them. The first is a base link to odom transform, and that kind of just comes from your odometry. So that's telling odom should ideally be centered at where you started, and that's just going to tell you how far your robot has moved since you started. So you can see here in the image on the left, the little coordinate axis on the left, that's the odom transform. So that's just like, that's basically the origin, 0, 0, 0, and its normal orientation. And then we have the transform on our right in the middle image. That's going to be our base link, the base of the robot. And you can see the coordinate axis is rotated a little bit, and it's moved away from it. And by calculating how this axis is rotated and moved differently from this axis, we can kind of tell where the robot is. And then from where the robot is, we can figure out where all the pieces on the robot are. And this is really necessary for navigation because we need to know where we are. And this is how we kind of get that best guess that I was talking about earlier. So yeah, those are the prerequisites. You need to do at least this stuff in order to get this working for your robot. And there's a considerable amount more for getting your robot set up. But as long as you're publishing this, you should be good to use navigation. Okay, so this demo, we kind of have 2 goals in what we want to do. The first is SLAM mapping. So SLAM is an algorithm. It stands for simultaneous localization and mapping. And essentially what it does is our laser scan is going to be shooting out lasers into the environment, essentially. And what the goal is when our robot moves, those points are going to shift, all those laser scans. We want to figure out how far a robot moved based on how those points move. That's kind of the idea behind SLAM. And by doing that, not only can we figure out where our robot is, but we can create a map of the space. You can kind of see it here, right? Like, it's not fully mapped out, but the long parts at the bottom, those are where the lasers kind of shot out and bounced back to the robot. And it's telling the robot, okay, there's a wall there. But it's not fully mapped out because they haven't moved around it. But this center space, they've moved around a ton, so they can kind of see all the walls. And that's kind of the idea behind SLAM. We'll be going into it a lot more later, so if that's a little bit confusing, don't worry. And then the second part is AMCL navigation. So the first half is teleoperation. So someone has to be controlling the robot manually. Like, I'll be using my keyboard to move the robot around the simulator. The second part is totally autonomous. All we do is give it a coordinate in the map, which you can kind of see at the end of this green path. And what it'll do is it'll create a path, this green path, and it'll follow it so it gets to its final destination totally without any control from us. So it'll move around, avoid obstacles, everything you'd really want it to do just by itself. And that's really nice. Like I said, this isn't the only way to do navigation. You might think of like autonomous cars, right? They don't have a map of their space beforehand that they can navigate upon. So this method wouldn't really work because they don't know where they are. So they have to use some other methods that are related, but I'm not really going to go into them right now in order to navigate around their space correctly. Alrighty. Does that make sense to everyone? Does anyone have any questions before I continue? Because I think we're going to go on to the demo part, which should take a lot longer because there's a lot more stuff to talk about. Alrighty. Okay. So time to start the demo. First things first, you might see I'm on a Windows environment, which might be surprising if you know ROS. What I'm going to be using is something that's recently been built into Windows called Windows Subsystem for Linux, which essentially is kind of what it sounds. It's a Linux environment that's totally built into Windows. So I have this terminal here. This is totally Linux. And the only thing I have to do is I have this special program called MOBA Xterm that allows me to run graphical applications from this. But besides that, everything else is in Linux. So it kind of, I personally prefer using Windows like every day. And this allows me to still use Linux when I need to do something related to program. And this will not run on Windows at all. ROS is on Windows, I think, but I don't think it'd be safe to assume that any of the code I'm going to write would run there. So yeah, Linux necessary. And if you're interested in this, I've been really happy with this. It's a great way to run Linux if you still want to use Windows. If you're interested, you can contact me or just look it up and get it installed and start working with it. Okay, so first things first, I'm going to show off what we're going to start with, which is just the robot in Gazebo being able to navigate around. So if I go to my my workspace, this is my Catkin workspace. That's where everything ROS goes. All the packages you install, all the code you're going to write is going to go in this Catkin workspace. I'm going to source something called the setup file, which essentially is made. Where am I? Okay, I got a Catkin make, I think. Okay, give me a second. I don't know why it's not working. Oh, I know why. I was giving it the wrong path. My bad. So yeah, I'm going to source something called the setup file. And this essentially gets all of the environment variables that ROS kind of builds on its own and whatever other details it needs set up for your terminal environment. Without this, ROS really wouldn't know where to find your files. And there's a lot of nice commands that ROS can do that kind of this is necessary for. So every time you build your environment, make sure to do that. And then what I'm going to do is I'm just going to run our launch file. So this kind of just launch files are like essentially the heart of ROS. You run them and it can do a whole bunch of things, run a whole bunch of different services and anything you want it to do. So I wrote a little launch file before this that essentially just launches Gazebo, and we can also navigate around the environment. So I have to nav tester, which is my package that I created, and then telly up. Okay. So everything's starting up. Awesome. So this is our Gazebo environment. I'm just using one of those sample worlds. It's a little corridor that we can map around in. This is the TurtleBot. You can see it looks exactly like it does. It's a Roomba with a Connect on top of it. And if I pull up the terminal, I get a nicer view of this. I can use the keyboard to, oh no, the keyboard to move around. Simple. And nothing else is happening. All right. We're not doing any navigation. We're not doing any mapping. This is just kind of the basics prerequisites that we need to start doing this, right? Imagine this is like my robot in the real world that I would be testing on if you weren't under quarantine, right? So yeah, this works pretty convincingly, but it's not that interesting. It's kind of bland. So let's get onto the mapping part. And I'm going to kind of walk through my process and talk through what I'm doing. If you guys have any questions, please feel free to ask. If I assume something about ROS that you don't understand, please feel free. I'll be happy to explain it. For some reason, Gazebo does not like to close sometimes. It'll just sit here and wait until, for some reason, there we go. Okay. So let's move into my package. ROS packages are kind of just collections of code that do things. So this is my nav tester package. It's where everything that I want to write will go in. Okay, so before I do this, actually, I'm going to remove source because that's where my old code was in there that I don't want to work with right now. Okay, so I'm going to go to nav tester. And then this is, you really have full control over the directory here. For good practice, typically you put your launch files in a directory called launch, pretty self-explanatory. Yeah, and then here we can create our file. So I'm going to switch to VS Code now just because I don't really want to be typing in terminal the entire time. So what I'm going to do is I'm going to create a file called slam demo.launch. And this is the launch file that we're going to use to use Slam. So launch files are just glorified XML. They're actually literally just XML. And if you know what that is, it's just like a markup language, kind of like HTML, if you're familiar with that, but different. So we're going to be using tags just like you do there. It'll look pretty familiar if you've ever used HTML, with different keywords and different uses. Okay, so give me a second. Our first thing we want to do, we need to open the gazebo environment every time we do anything with it. And the nice thing is with launch files, you can nest them. So all I really have to do is call include, and then give me a second. I need to minimize something. There we go. Include, and then we can say file is equal to, and then we can just say go find the file path. Now, these launch files offer a lot of nice tools where you don't have to like give exact paths or anything like that. We can just say find nav tester, and this is going to give us the path in ROS in my file system to my nav tester package. And then we just have to tell it where in this package is the launch file we want to use. So it's in /launch/teleop demo, because that's what we were just running. And this will launch all the gazebo stuff and get teleop working, which is just robot control and everything we want to do. So that's perfect. And then close our tag. The other thing we want to do before we start working on Slam is we want to get a visualizer working. So in Gazebo, you couldn't really see, for example, the camera or the laser scanner, anything that we're doing. So we're going to use a separate application for that. It's called RViz. It's just a visualizer. Those photos that I got on the slideshow were from that. So what I'm going to say is include file. Again, it's the same idea. And I'm going to use a visualizer provided by Turtlebot. You can make these in RViz pretty easily. It's not too big of a deal. But I'm just going to say find Turtlebot RViz launchers. And that's where it is. Launch/application.launch. Okay. And this is going to allow us to better evaluate what our program's doing and kind of see what's going on. Okay, and lastly, we want to actually do Slam. So there definitely is a lot of ways you could do this. But the simplest way is just to run the node, the Slam node, the gmapping Slam node, which is the implementation of Slam we're going to use. Nodes are kind of like just the lowest level of programs you can go in ROS. These are what actually execute code. So nothing I'm doing here is really writing my own ROS code or anything. I'm just kind of using other people's things they've wrote and configuring them and making sure they're working. Nodes are where you really get into the thick of things and write your own stuff. If you're using other simulators or writing your own robot, you'd probably want to get into that. But because I'm using the simulator and I already have all that set up, I don't really need to worry about it, which is really nice. So I just say node. I have to give it a package, which is just like nav tester, the ROS package where it's stored, that's gmapping. Type is, there's like subnodes essentially that you can go into. It's just like another way for organization. Slam gmapping, I can't type. And then the name, which is also happens to be slam gmapping. And then output equals screen. That's just for debug output, but it's nice to have. Okay, so this is our first pass at the Slam. This is it, right? Run Gazebo, run RViz, and then run Slam. Pretty simple stuff. So in order to actually get this built, what we got to do is we go to my Catkin workspace. First of all, I'm going to run install basic. On your system, what it would do is it would install all the dependencies and also set this in. First time you install anything, make sure you do it /installs basic. .sh. So this is gonna run, it's gonna clone a bunch of stuff. Install a bunch of stuff that I already have. And this is doing the part that I want to build. But if we just, for example, wanted to bring over just this package, we just copy my package nav tester into the source directory. So copy recursively nav tester source. So it's going to put nav tester in the source folder. Awesome. And now we're ready to build. So the command for building here is catkin make. Catkin is their build manager, kind of like CMake or anything you've used before, but this is just what they call it. And then a whole bunch of things will happen. This is all of the dependencies that we need, plus some others in case you want to experiment with TurtleBot. Takes a couple seconds, maybe 10 or so. Hopefully it'll finish soon. Yeah, and once this is over, we can actually test our SLAM implementation. And hopefully it goes well. We'll see. Yeah, and I'm by far no expert in this stuff. I started doing this like about maybe 3/4 of a year ago. So I'm just kind of my goal with this is to walk you guys through how you might go around learning some of the lessons that I've learned. Maybe you don't have to go through all the trouble that I went through. And if you're interested in this stuff, give you kind of like a head start on experimenting with it. But nothing really can replace just getting your hands dirty and working with this stuff and understanding how it works. Almost done. The reason it's taken so long is because I had to build the entire source directory again. It'll be quicker next time I do it. So don't worry about that. All right, awesome. We're done. So now, just like before, we can run ROS launch, nav tester. But we have two choices here. We have teleop demo and slam demo. So we want to run slam demo, so let's do that. Oh, one thing, I know why that didn't work. So one weird, I don't know exactly why. One of the packages I'm using, so step back a second. TurtleBot is meant for older versions of ROS. And for some reason, one of the scripts in it crashes whenever you install it fresh. So it might just be on my machine. I'm not 100% sure, but it's a really easy fix. So I just have to change my directory into the ROS package or the TurtleBot package, the teleop. Go into the scripts folder. And there's this, for some reason, it's using Python instead of Python 3. And if you guys know, Python 2 recently went end of life, not being supported anymore. It's not even installed on my machine, I don't think. And that crashes when it tries to run it. So I just got to change that. And that should work nicely. If I just run the command again, ROS launch, there, no errors. All right. Also, you might be worried about seeing this. This is another artifact of ROS being for older systems. Essentially, it was doing a certain type of behavior, publishing repeated transform data that was accepted when it was made. Now ROS hates it with a burning fury. So we just get like a ridiculous amount of warning messages every time we run this for no good reason. It's kind of frustrating, but what can you do, right? Okay, so we see here, this is RViz. Right now, this is all basically RViz shows you what the robot knows. So it's not letting me navigate around it for some reason, but that's fine. Ooh, maybe it crashed. Ooh, it might have crashed. Well, okay. I don't have to move it around to explain a couple things. This white line on the right, that's the data from the laser scan, our fake LiDAR on here. So that's what the scanner sees. And then we have our robot centered at the origin of the map. And if we go in Gazebo, we zoom in, well, we can see it's in the right place, and all it's really seeing is a wall. So it's working good so far. If I... that's the wrong window. Okay, I don't think it liked when I did that. So let me just restart it. But yeah, RVision is really useful. There's a ton of different things you can do with it, ways to debug with it. I'll show you one of the things. So some background information on the TurtleBot. It doesn't actually have a LiDAR on it. It kind of uses, it goes from a depth camera to, there we go. It goes from a depth camera to a LiDAR. It kind of uses some smart processing on the image. So I can actually show you that. So RViz, basically it has all these types of visualizers that you can use. So if I go to add down here, there's a whole bunch of them, you know, axes, camera, depth cloud, for example. Let's add an image. So this image, if I go to the image topic, so this is the topic where that image is being published from the robot. We have two of them. We have a depth image raw and a camera image, or RGB image raw. So if you open up the depth image, this is all it sees. It's just it's a wall. That's really all it sees, because it sees the same depth. It represents it away. If we change this to be image raw, oh, that's the same one. RGB. There we go. And now it sees the wall. So things seem to be working well. Let's try moving around. Okay, so the robot's moving. But as you can see, things are not going so great. What's essentially happening here is our SLAM algorithm is freaking out. The way it works is that it's trying to match these particles that are on, or sorry, not particles, but it's trying to match the laser scan up with the terrain that it's seen before. And it is not liking this at all. It's jumping me around. If I start moving, it's going to freak out even more. So pretty obviously, this is not sufficient for mapping. Because the robot has no idea where it is. And this map is totally not recognizable to the gazebo map. But that's kind of my fault, because I didn't really set up SLAM. SLAM is not really a one-size-fits-all kind of algorithm, or at least this implementation isn't. You don't just plug it into your robot and it'll work. You have to change a lot of the settings. So let's go do that. Let's exit this, because that's not working, obviously. So what in ROS is best practice to do, because we're going to be adding a lot of parameters to this Gmapping SLAM package. I'm just going to make another launch file that we can include later that'll have all this code centralized. So I'm going to call it slam.launch. Perfect. And I'm going to copy this node in. I missed also, don't forget our launch tags. Okay. And a lot of this kind of figuring out, oh, wait, before we do that, let's include that in here. So I'm going to say find nav tester. So it's launch / slam.launch. That's including the file I just created in this launch file, and then closing. Perfect. Okay. So finding out what parameters here, I'll show you. What parameters we can change is really easy on ROS. Just go onto Chrome window, web browser, and look up the package itself. So if we look up ROS SLAM Gmapping, we can go to this Gmapping package. And for the future, if anyone's doing anything like this, this is great documentation. So it'll tell you what nodes it subscribes to, so what's required, what nodes it publishes to, so what data it produces. Services, we're not really going to get into, but they're like functions or similar. And then a bunch of parameters that we can change, a ton. And these are going to affect how the node runs. And in our sense, how the SLAM algorithm runs. So there's a ton of stuff. I don't really have time to get into them all, but TurtleBot comes with kind of a preset one. But I'm going to copy that over, and then we'll talk through some of the more important ones. Okay. So first things first, I just got to make this. Okay. So I copied in a lot of code. And then before we do that, let's give it a closing bracket. Closing tag. Awesome. So this is a lot of parameters. The nice thing to know is that, from my understanding, all of these were kept at default values, so those are pretty good. Was this the right one? Yeah. So I'll go over the ones that actually were changed and were deemed as valuable here. So the first one is configuring our transform names. So there's a lot of flexibility in ROS with how you want to name stuff. And this is just ensuring that Gmapping is referring to the same components we are. So the base frame is kind of the base on the robot. And we said, okay, we're using the frame called base footprint. And that's just like literally the Roomba is the model is called base footprint. And then the frame that ODOM is in, we called it ODOM. But I mean, if for some reason on your system you're referring it to like as, whatever you want to, you could just change it here. So that's nice. That's that. These are map initialization values. So if we open it up again, I should just show you. Give it a second. So all this yellow stuff is the size of the map. So this is essentially what it's going to be saving. And all those values do is it kind of initializes it to a smaller space, because it's going to be trying to do a lot of calculations over this entire map. So by decreasing the size, we can kind of, not only does it help with memory, it doesn't have to keep track of everything here, but I think it might also help the algorithm be a little bit faster and accurate. Okay, we have some laser scan settings. So this is going to be unique to whatever LiDAR or system you're using. Like I said before, we're kind of using this fake depth cam to laser scan kind of thing. So it's kind of pulling from the depth camera. And that's where we got these values from. So this is the max range is going to be... Oh, sorry, I guess I should have went over this. Yeah, it's just the X-min and the Y-min of the map and the X-max and the Y-max of the map. So saying how big the map can be. Okay, to go back to the laser scan. The max range is how far the laser can reach. And max U range, I'm actually don't know it off the top of my head. What the difference between max range and max U range. So the max U range is the max usable range. What is max range? It just seems like they're different. So this is like what happens with LiDARs if they're lasers, right? So what max range is essentially saying how far does the laser have to go before we assume that it doesn't bounce back? Because like what happens if you send a laser out and you never get the laser back? Your LiDAR is not going to know how far it went. So I believe most LiDARs will say that's infinity, because it never got the laser back, right? So it could technically be infinity. So this just kind of caps that. It says, well, it can't be, the LiDAR can't have a value higher than whatever we set this. So we set these to 8 and 6 meters respectively. Again, if you have your own system, this is probably worth playing on. If you're using someone else's, this probably is already set for you. And I just passed all these parameters to this node. So essentially what I'm saying is all of them have the default value, 0.005. We're just saying, okay, set them to be this. And then I have these down here. It seemed like it was working better when I had these just in my testing. So, it might be superstition speaking, but I just kept it here. It makes me feel better. But this is really the stuff that's deviating from the default values. This is really what matters. Oh, and then I missed one. So this is going to be actually what's affecting our SLAM algorithm. So minimum score, I actually had this change. I was playing around with it. I think they have it set to 2000. I upped it a little bit. This is a score that represents how well SLAM thinks it has matched the terrain. So when I turn around, right? Okay, so let's create a little bit of a map in here. Let's see if I can get it to map without flying around. Okay, so, okay, it's doing it. When I, for example, turn the robot clockwise, it's getting this new section of terrain. And the score for scan matching represents how accurately it thinks that it's found new terrain, or that it is found terrain that you've already traversed upon. So really what's going on here is I'm turning left or counterclockwise in this example, and it sees more flat wall. This flat wall, it just thinks it's already the flat wall we've already seen over here. So it says, okay, the robot must have magically moved somehow. So it sets the bot all the way to the left because it assumes that it's right. With a minimum score, we can say no, unless you have this amazing score for your scan matching, you're like 100% sure that the terrain we're seeing is the terrain we've already seen. Trust the odometry. The odometry, right, is how far the robot thinks it's moved. And we're just saying, you know what, believe in it for now. Don't move the robot around because you think you see new terrain. Just trust the odometry and keep the robot where it thinks it is. That's minimum score. Let's go back and look. We also have the number of particles, so this helps with estimating the position again. I don't want to go into it mostly because it's a little bit above my head, but both the AMCL and SLAM uses a particle filter to accurately demonstrate or accurately estimate where it is. And this just changes how many particles it's going to be estimating. The higher you go, it's going to be more intensive on the CPU, but it might get a better representation. Not 100% sure about how it affects it here. It's more obvious in AMCL. And then this is just how quickly it updates. So linear update, if I move forward, I'm not on the wrong thing. If I move forward, if I move forward some distance, it's automatically going to force a scan update or a mapping update, no matter what I do. It's not doing it right now, but okay, there we go. See, there was an update with my position. So what this is just changing is how far you have to move before it updates. And then angular update is how far you have to turn before it updates. So we're saying 0.5 meters and I believe 0.436 radians, which is probably some factor of pi. Maybe pi over 8, I don't know. But yeah, so these are the settings that we're going to use for SLAM. This is what I found to be good. And we already kind of have everything set up there too. So all we have to do is call it or run it, build the files again, and then launch it. So that'll take a little bit. Any questions that I can answer while I'm waiting for this to build? So yeah, it's going a little bit faster this time because I already. Ooh, that was really quick. Oh, I didn't copy it over. That makes sense. So I have to copy, like I said, copy nav tester into source, and that'll tell Catkin, okay, I need to check everything over and do all this over again, which is kind of annoying, but it makes sense. There could be interdependencies that you're changing, so it has to build everything. What else can I talk about while I'm waiting for this? This is pretty easy to get into. I would highly recommend. There's a lot of tutorials even beyond this for the Turtlebot. If you're interested, this is a really good starting spot to start learning. So I would highly recommend if you're looking at this stuff and going like, oh, I would love to learn how to do this to get into it here. Okay, so let's launch. No. Tester. And it's the same file. It's just the SLAM. Wow, I'm illiterate today. Oh no. What did we do wrong? Line 45. I must have done something wrong here. There we go. Gotta have a closing tag for the launch. Now to go through the process again. Yay. Yeah, and I've also went through the experience of using other simulators. Gazebo works really well with ROS. It has a lot of good interactions. I also tried using Copelia Sim. I did not have nearly as nice of an experience to do the same thing. I did learn a lot about it though, so that was nice. It's a good experience there. And unfortunately, kind of due to COVID, I have never actually tested this on a real robot. So I hope to do that soon. That would be nice. Okay, so now, hopefully, it's not perfect. Slam is definitely error prone. But if I slow the robot down a little bit, we should be able to generate some decent maps. So if I start moving around, it should start generating a map. Hopefully, if it ever wants to. Perfect. And as you can see, the robot's not really jumping around as much. It hasn't that at all yet, actually. Oh, and there goes a huge chunk of the map. Let me increase the speed a little bit more. So, and here, while we're here, let me add an image. Okay, never mind. Let's just finish mapping. So I want to get a decent map done because this map is necessary for actually doing the AMCL, the navigation section. So I'm noticing I'm a little short on time, so I'm just going to cut it short on the map. But as you can see, none of the same problems we were having before. It's working really well, honestly, better than I had my testing. I was jumping around at least a little bit, but I don't think the robot has like wrongly corrected itself once. So I'm just going to get to the end of this corridor. And you can see on Gazebo, it's matching it perfectly. Get to the end of this corridor, and then we can save the map and start working on AMCL. All right, so there we go. It sees the end of the corridor. Now we're just waiting for the map to update. Perfect. And here we're pretty good to go with Slam at least. So in order to save the map, you have to run another node. And the best way I found to do it is just use another terminal. So first things first, source devel/setup to make sure we actually have all the things. And then there's a command we have to use. ROS run runs nodes directly, where ROS launch runs launch files. So kind of like how Slam is a node. We're going to use ROS launch to. Okay. So I'm going to use this command, ROS run map server map saver. So this is going to get the current map that we've created and save it to a file called my map. So if I run it, it wrote the map, it wrote the map occupancy, and now we're good to go on it to AMCL. Perfect. All right, so same thing as before. We're just going to create another file. Let's call it AMCL demo.launch. And there's a very similar idea, right? We're just going to have launch. Actually, let me pull my reference up real quick because there's a lot of stuff to write here. Okay, we're going to have a launch. And the same thing as before. In fact, I'm probably going to copy some of the code here because it's very similar. I'm going to run the same world that we used in Slam demo. The only difference is I don't want to use teleop because it gets in the way of the navigation controls. So I'm going to use this. Oh, wait. That's not the right thing to copy at all. That's not the right thing at all. Oh, no, it is. I don't know what I'm talking about. So I'm just going to use this argument to say don't use teleop. Use teleop false. So now we won't be able to control it, but that's good because that's not what we want. We also have to actually run our map server. So first of all, we have to create like what's called an argument. This is just like a variable essentially. And this is going to store the map that we just created. So we're going to say find map tester. And we're just going to say, okay, go directly to the mymap.yaml, yet another markup language, the map that we just created. Perfect. And then we're going to start up the map server node, which is the one we just used to save it. So same idea. Forgive me while I type this out. Same thing here. Name is map server. Package is map server. Type, guess what? It's map server. And then we're going to pass an argument in, which is what we just created. So we're going to say args equal to, and then we can kind of just say the map file argument that we already had. Perfect. Okay, so now what we want to do is actually get the AMCL node running. So what I'm going to do is just like with Slam, I'm going to create a new file called amcl.launch. And this is the TurtleBot's, from what I can tell, the best setup for navigation. Again, I don't really have time to show it, but if I ran navigation just with the node itself, things would not go well. It would not navigate well. Here are just a bunch of arguments that can be set outside of the file for convenience. There's a lot of the default values. Again, we have our laser scan settings, which kind of we can configure depending on how our laser works. Here we're going to set our initial pose. So basically, where we start at 0, 0, 0, and no turn. So we can just keep it as zeros, which we do in the file. Okay, we haven't called it yet, but we'll just set all these to 0. This is more setting the correct topics, so telling ROS, okay, I want you to look on this topic for the scan, etc. And then these are the actual parameters that we're going to use to affect the AMC algorithm. So the particles here is basically how AMCL figures out where it is. So it's adaptive, so the number of particles can change, and we're just bounding it to be between these two numbers. KLD error is kind of hard to explain. I'm not 100% sure what it does. I guess I can go to the page and let you know. I think it's just so it's for the... Yeah, so this is just the maximum error that your estimations can get away from, like, the actual what it's sensing. So having it at a higher value means we can actually drift more, which might help us in navigating better. This is just saying what components of the laser scan we want to count more. Again, this is more of the Massey side. I'm not 100% sure why these values are best. If it's a little bit above my head. This is just how quickly distances and things like that are updated. So similar to the, you moved this much and it updated, similar to that concept from Slam, the, where is it? The linear update and the angular update. And then transform tolerance. This is how, if your transform gets far enough away from where it thinks it should be, this is the value that controls it. It'll kick some routine in that'll help fix that, and this is the value that it cares about. Okay, I think that's everything here. And again, these are just default values that make me feel good because it works. Okay, so again, we have to call, or not call, but we have to start up that node in our launch file. And this is a little bit more, so I'm just going to copy it in again. We create a bunch of args, initial pose X, initial pose Y, and initial pose A. We set them all to 0, like I said before. And then all we do is we start up our AMCL file with these arguments set. Okay. Next up, navigation is kind of a two-part idea, right? So you have AMCL telling you where you are. Next, we got to create a planning system that allows us to move the robot. So we're going to be using something called move base. This is just helping us with creating path planners. If I have time, I'll go into a little bit more, but I want to make sure we actually get to seeing this working. So I'm going to rush past this a little bit, but basically same idea. I'm going to create another move base.launch file, and here we're going to configure all the settings for the move base. To go over this a little bit, we don't need this. I forgot to remove that. Again, we have some more arguments for changing the topics that it wants to refer to. These are all the parameter files that come with Turtlebot. A lot of this, because it's dealing so much with the movement of the robot, is heavily based on your base, what robot you're using. And if you want to work with these, you're going to have to look into them. There's a ton of information on how to manipulate them and what to put in them. And honestly, pretty good defaults. I think a lot of these are pretty default. So look on those yourself. This is the same idea as before, telling us which transforms are what. And this is remapping some topics to another so that we can get them in the right format. Some nodes might be looking for topics in certain places, and this is making sure they get the information they need. Okay, so we included that, and we're almost there. The last thing we need to do is, just like before, we need to include our visualizer. It's the same one as before, and you just got to copy it in. Okay, and then end our launch file. Alrighty, I think that's good. Hopefully this runs on the first try, but with my luck, probably not. Oh, we got a cat can make. I'm losing my mind. Okay, so cat can make. AMCL, this part's a little bit more complicated, but essentially there's two parts, like I said. You have AMCL, which is figuring out where the robot is. It's creating a local and a global cost map of the environment. So a cost map is just essentially an array of numbers that tells you a higher, for I don't know which way it's ordered, but for example, a higher number says, don't go near this place, there's an obstacle. A lower number says, there's no obstacle here, you're safe to navigate around here. And then we're just going to have a path planner that uses that cost map to plan an efficient route through it. And it's a little bit more complicated than that. I'll show you what I mean, but let's hope this works. So just like before, we're going to run AMCL demo.launch and pray. Uh-oh. We got an error. What did I forget? Oh, no. Oh, there it is. Yeah, this is the most fun game with this setup because you can't see anything. It's great. Okay, wait, we're getting close. Okay, we're at the make. All right. Cannot launch node of type map server. Okay. Maybe I forgot to check it out, but here, wait, let's go check out what I did there. Oh, because there's a plus here. Yeah, that makes sense. Probably should have checked that before. Yeah, and unfortunately, building this is kind of a lengthy process, but it's not too bad. And I really wish Gazebo would close because we are close to running out of time, and I don't want to try and avoid going over. There we go. Come on. There we go. So copy it over. Cat can make. Run this. Yeah, if anyone has any more questions about this, please, floor is open. Let me know. This might take a little bit.
What was the thing you used for Linux called again?
Windows Subsystem for Linux.
Yeah, that.
Yep, I love it. It's great.
What was the program you used in specific?
Oh, so the program is, so I have Ubuntu on Windows Subsystem for Linux.
Right.
And then to be able to run graphical programs, I use MOBA Xterm.
Okay.
Okay. Please work. Let's go. Seems like it worked. So you can see here kind of how AMCL works. These are all the particles that we talked about. These are estimates of where the robot thinks it is. And then these are part of the cost map. The cyan and like red and purple, those are the global cost map. And what we do is we click up here. We say, give a 2D nav goal. Click it over here. And it'll generate this local cost map, which is a lot more detailed. and generate a path plan that starts moving the robot there. And pretty much that's it. That's how it works. You can see on Gazebo, it's pretty accurate to the real thing. Yeah, and that's AMCL navigation. That's the basics of it. If you do something like this for your robot, you should be able to get it going. Some notes about it. You can see here, like I said, there's a difference between the local cost map and the global cost map. This little red line is the local one that can actually deviate from the global one, but it's just to help with planning better. And here's a good example. The robot doesn't really know where it is. It kind of got lost here. So it's doing a spin to try and figure out, okay, let's make 100% sure I am where I think I am, and then it'll continue on his path. And we can send it into uncharted territory, but it kind of thinks of this empty space as like empty floor, so it won't go there, but it can kind of make its own guesses if we path it onto this dark green stuff. Yeah, and that's really AMCL. Very useful for navigating and mapping an environment. Nicholas, you said what websites and channels are good places for tutorials on this? I would just recommend ROS has, if I go to Turtlebot tutorial ROS, this is kind of like their intro tutorial. It doesn't really go deep enough in it, but if you just want to get this set up, this is a really, really good place to start. Let me send it in the chat. Okay, well, the chat disappeared, and I don't know how to get it back. Give me a second. There we go. LearnTurtleBot.com. Great place to get started on it. And besides that, that's everything I really want to talk about. I'll stick around if anyone has any more questions. Otherwise, thanks for coming today. I hope you enjoyed.
Thanks, Jack.
Yeah.
Thank you. Have a good day.